Hi, my name is Marcos Saraiva. I'm a master's student at Computer Science Department at Federal University of Espírito Santo, Brazil, and I'm also work as a reservoir geophysicist at Petrobras. The title of our work is Data-Driven Full-Waveform Inversion Surrogate using Conditional Generative Adversarial Networks. Those are my co-authors, Avelino, Josi, Del Rey, and Thomas. Here, a brief summary. I'm gonna pass by all these topics. Oil industry use reflection as a primary indirect method for investigating the properties of the subsurface. This method uses a controlled source of acoustic waves and receiver arrays, hydrophones, to record the transit time and amplitude of acoustic waves reflected by contrasting rock types interface. Like here, the acoustic wave comes, and when it reaches the interface between two different rock types, it is reflected and recorded by an array of sensors. It is actually like a huge ultrasound, but instead of a baby, we are trying to find an oil reservoir. Here is the final result of a seismic acquisition. After processing, we have the seismic data. This is a real inline from Santos Basin, Brazil. Source is National Petroleum Agency, ENP, from Brazil. Here, the same section interpreted. You can see that you can identify the oil reservoir and decide if you put a well or not, the best position, the volume, etc. Seismic processing needs a volume called velocity model. It's very important. And a typical workflow for seismic velocity estimation consists of these three steps. Those are sequential. First, we find the normal move-out velocity estimation is manually processed. So you input this low frequency velocity into the second step, is the ray-based or grid tomography, and it will deliver a velocity model, an interval velocity model with a little bit more frequency, but still low frequency, typically up to 2 or 3 hertz. And finally, we have the full waveform inversion, for short, FWI. It is a seismic inversion technique that uses pre-stacked seismic data, the raw data from the acquisition, to output a detailed interval velocity model. Here, an example of the initial step of the FWI, in which it takes initial low resolution from the seismic tomography, and simulates using numerical methods, numerical modeling, and wave equation. It simulates a seismic acquisition and compare with the recorded one. It's an iterative method, and after some updates, the final seismic velocity will produce a seismic that matches the recorded seismic. So we have an interval velocity model from the FWI. The FWI is important because it fills the gap between the low frequency tomographic velocity model and the seismic reflection image. So we increase the useful bandwidth. Now let's talk about GANS. GANS are generative adversarial networks. They stand out for their ability to learn how to mimic data provided to them by capturing their statistical and spatial distributions. GANs were first proposed by Goodfellow et al. In 2014. And there are two networks that compete each other, the generator and the discriminator. We can see GANs as a two-player game. We can think the generator as an art forger and discriminator as a detective. The detective will try to identify if the artwork produced by the generator is real, if the artwork is real, comes from a museum, or if it's fake, it comes from an art forger, in this case, the generator. At first, the discriminator learns fast. It's easy to know because generator produce poor results when compared with the real artwork. So it's easy to know if it is fake or if it is a real one. But with the feedback from the detective during the training, the art forger starts to produce very good results, and it is hard to distinguish between the real or fake artworks. This is a real artwork. This is a real forged artwork. It was sold for $10 million. We use in this work a conditional GAN, pix to pix. The idea is the same, but we have a conditional. Image is used as conditional. In this example, we're trying to transform maps into satellite images. And G tries to synthesize fake image that fools D, and D tries to identify the fakes image. Here we have some applications. The objective of a conditional GAN can be expressed by this first equation, where G tries to minimize the objective against an adversarial D that tries to maximize it. Previous approaches have found that it is beneficial to mix the GAN objective, the GAN loss, with the traditional loss. In this case, we use L1 loss because it encourages the less blurring. So this is the final result. Materials and methods. We use marine seismic acquisition from campus base in Brazil, and 4 volumes. The first one was the post-stack seismic image. This is the seismic volume, an average tomographic velocity, a two-way time grid, just the grid of the seismic volume, and FWI interval velocity. Here is how we divided the data for training and validation sets. 30 and 70% of the data respectively. For the training set, we randomly sampled 2,000 patches, and for validation, 800 patches, both with 500 by 500 samples of size. We combined the first 3 volumes in a 3-channel image. We combined seismic amplitude, average tomographic velocity, and two-way time grid, and create this pair. It's a training pair in which we have these combined inputs, the combined channels in one input, and the FWI as one channel as desired output. Here is the architecture. We have a generator, this is a UNet with skip connections. And here is the discriminator, is called patch GAN because it subdivided the image, the paths in sub-paths, and classify individually each one of these patches as real or fake. The best metrics we found was the visual analysis performed by a trained geophysicist, but we also use a percent error, the traditional percent error, and an index called structural similarity index measured that takes in account the mean, the standard deviation, and the correlation between the two signals. At first, we tried as input only the seismic amplitude, only one channel, but we got poor results. We got some artifacts, as you can see here and here, and we could not capture the lateral variation of the velocity. So we insert 2 more channels, as I shown before. the average velocity from tomography and two-way time grid, and the results were the results are here. The FWI velocity is almost the GAN generated velocity is almost identical to FWI. We also got good metrics on percent error and SSIM. The shallower patches presented better results than the deeper ones, visually and in the metrics, but this was expected once the traditional FWI present worse results at deeper regions. The output matched the validation set distribution really well. Here we have a histogram of in blue from the FWI velocity and in red from the GAN velocity. They are almost identical. The percent error over the training, over the epochs, you see it stabilized fast. And the SSIM over the epochs, the same. They are really close. Here we have a zoom. Discussions, previous works show the feasibility of using convolutional neural networks for one-dimensional synthetic seismic inversion. Other works use pre-stacked seismic data, a 3D pre-stacked seismic data, and cycle GANs, but also a synthetic data, and they achieve just qualitatively moderate results. In this study, we apply a conditional peaks-to-peaks GAN to generate a high accurate velocity model using real data, real post-stack seismic data, and multiple inputs. Here is the big difference. Neural networks are understood to perform better at interpolation than extrapolation. Therefore, it is a challenge for a conditional GAN to extrapolate to lower frequency if we use only the seismic image reflection like here. However, it becomes easier to interpolate the missing frequencies, the FWI, if we combine a lower frequency data input, in this case, average tomographic velocity and two-way time grid, these two channels, additional channels in the input. This explains why adding more information helped to improve the results. The L1 loss acts as a global metric, minimizing the average loss of all pixels, where GAN loss provided by the patch GAN discriminator focus on high frequency structures. We suspect that the reason the experiment using only one channel presented good percentile error and SSIM values was that the generator produced a velocity field that honors the low frequency associated with the average velocity, good percent error, and the high frequency variations, good SSIM, however, producing a poorly accurate visual results. This result reveals the difficulty of finding a reliable metrics for evaluating GANs. We have present a method based on peaks-to-peaks conditional GAN with multiple inputs that can be used to surrogate FWI velocity model. The three inputs were vital as the experiment using only one channel failed. Further development architectures focused on the seismic data particularities, considering three or more spatial dimensions may generate an improvement in this quality of our result. The test data presented excellent results based on visual analysis and percent error or SSIM metrics. The main geological structures were and lateral velocity changes were captured by the resulting velocity model. And once we trained the GAN, it was really fast to generate the FWI interval velocity model surrogate, almost real time. Therefore, our proposed method can replace the FWI modeling or provide an initial model that will need fewer iterations to converge. This proposed method, when deployed, has the potential to speed up the geophysical reservoir characterization process, saving time and reducing computational resource requirements. Thank you for your attention. Any question, please contact me.